Hello everybody and welcome back. Today we're going to be looking at Big Ideas section 6.4 in Algebra 1. So last time we talked a little bit about exponentials. We talked about exponentials in terms of the form ab to the x power. We talked about how to use that formula to basically predict exactly how many of something there will be given a certain growth rate. Now, it's important to take a look at this formula again, because this formula is still what we're going to be using today. Y equals a b to the x, where a is our y-intercept and b is our growth factor. But we're going to get a little bit more specific this time. You see, last time we talked a lot about what is exponential growth, what is exponential decay, and so on and so forth. Today we're going to get a little bit more specific and figure out equations, or I should say functions, to use when we want to find specifically growth or decay. And spoiler alert, they will look extremely similar to this one. So let's get started by talking a little bit about exponential growth. In our last lesson, if you don't mind me flipping back to that, in our last lesson, 6.3, when we talked about exponential growth and decay, we talked about it in a context where we were trying to figure out what happens when our a and b values change. So we said that the b tells us how much the curve there is and whether it's increasing or decreasing. We mentioned that growth happens when b is bigger than 1, and decay happens when b is in between 0 and 1. That's why we have these graphs up here. These are graphs of growth on the right. Let's focus in on growth just a little bit. Focusing in on exponential growth. Exponential growth is when a quantity increases by the same factor over equal intervals of time. When a quantity increases, and I want you to underline increases, by the same factor over time. The reason why I'm talking specifically about increasing here is because we want to be as specific as possible when talking about exponentials, because these can get either very big or very small. We want to make sure everyone knows what we're talking about. When we say increasing by the same factor, for instance, we mean you start with a number and you're going to multiply it by the same growth factor every single time so it gets bigger and bigger and bigger. For instance, if we started off with the equation y equals 3 times 2 to the x, this would be us saying, okay, take 3, multiply it by 2, then multiply it by 2, then multiply it by 2, then multiply it by 2, over and over and over again, x times. That's what we mean by growing by the same factor. We're multiplying by 2 every time, so it's growing by doubling every single time. Now, there is one specific caveat we talked about last time, and this is of the utmost importance. When talking about exponential growth, your b value must be bigger than 1. If it is not bigger than 1, it is not going to grow. We talked about this with the Desmos activity last time, but specifically, in our notes, we said that b has to be bigger than 1. So let's see if we can take this and put it into practice a little bit. I've got a problem set up here with exponential growth, and I want to see what we can figure out from it. From there, we'll figure out the general rule for making an exponential growth function. So here's the situation, and you don't need to copy this down, but I do want you to try it in your own notes. In 1972, there were only 31 bald eagles, in Michigan. This is a true fact. However, due to conservation efforts, they began to grow at a rate of around 17% every year. So we started off with 31 eagles, and then their population grew by 17%, and by 17% again, over and over and over again. Now, some things happened which took the population down a little bit, but let's pretend for a second that the population was left to grow at this rate. We kept on growing by exactly 17% every year. My question is, how many bald eagles would be in Michigan now, in the year 2022? Well, you've got a lot to look at here. If you recall from last lesson, we discussed the form y equals a times b to the x. And I'm putting b in parentheses because I want to put a number in there. A is always going to be your starting value, or your y-intercept, and b is how much you grow by each time. So, how much did we start with at the very beginning? Well, we started with 31 eagles. So that's going to be our a value. Y equals 31 times b to the x. But here's where we encounter our first little problem. It's a problem where we have to figure out what is realistic. Let's start off by looking at the rate, or how much we're growing by. Notice it doesn't tell us a growth factor here, but it does tell us that we're growing at 17% each year. This is very useful because it tells us how much we're growing by. That's kind of like a growth rate, isn't it? Like a growth factor? But we can't put 17 in here because we don't like using percents in our equations. Instead of putting 17%, we need to turn 17 into a decimal. And this is a skill that many people might have forgotten. To turn a percent into a decimal, there are two ways to do it. First off, percent means per 100. Percent, per 100. Cent means 100. So if we wanted to, we could divide 17 by 100 and get our answer. 17 divided by 100 is 0.17, and that, or 0.17 more specifically, that is how we could represent it. However, another trick to use that some people may remember a little bit better is the moving decimal. To turn a percent, like 17%, into a decimal, put your decimal point where it should be in the percent, and move it over twice to the left. That'll give you 0.17. To turn 0.17 back into a percent, you can move the decimal twice to the right, back to 17. Either way, no matter how you decide to calculate this out, it looks like our decimal is 0.17. So surely we can just put it in here and call that a day. Those keen-eyed observers may recognize something wrong with this. And I want you to keep that in mind, because this is absolutely not correct. But we're going to show you why, so that you don't make the same mistakes. I guess the last thing we need is to figure out what x is, or how many times this growth factor applies. Well, this is tough, but we start in 1972. We go to 2022. How many years are in between 1972 and 2022? To figure that out, to figure out the difference in years, we can always subtract the 2 years. So what's 2022? Whoops, sorry here, everyone. What's 2022 minus 1972? We get 40 years. So this should be taken to the 40th power, right? This x should be 40. Let's see what happens when we try taking 31 times 0.17 raised to the 40th power. I'm going to bring out my iPhone calculator because I know that many of you do not have official calculators at home. While you do need one for your later math classes, and the earlier you get it, the better, it is important that we are able to do this math here today. So if you use an iPhone calculator or an Android calculator, you can follow along with this as well. First things first. Looking at this problem, we see that we have 0.17 to the 40th power and 31 times 0.17. Using PEMDAS, we have to remember which one we do first. And it turns out we have to do this 40th power, which I'm going to rewrite because it looks a little messy. We have to do 0.17 to the 40th power first. Exponents, e, goes before multiplication, m, in PEMDAS. But how do we take this to the power in our calculator? Well, by turning it sideways, you'll access a lot more possibilities. I'm going to type in 0.17, and to take something to a power, in an iPhone calculator, it'll be this X to the Y button. If you use Android or an actual calculator, your button may look something like this instead. A little caret is what we call it. Either way, we're going to take 0.17 raised to the 40th power. And we get something that looks like this. Don't worry about this for now. It's not going to make sense for a second. If we then multiply by 31, oh, it's still nonsense. This is something that you might have learned in middle school, but probably not. This is called scientific notation. And the E with a number after it tells you either how many zeros are after it, or if it's a negative number, how many zeros are before it. So this number will give us something along the lines of 0.000000000, 30 zeros, because of the negative 30, 512. Does that make sense in terms of a number of bald eagles? No, and on top of that, wasn't our population supposed to grow every year? Not shrink to be like a decimal. It seems like our normal approach is not enough to guarantee that we are exponentially growing. Our normal approach does not work in this scenario. AB to the x, you have failed us. Well, maybe not all the way though. See, AB to the x does work for all exponentials. A will always be our starting value no matter what, and that will always work. But it's our B value that's messed up. I hinted at it earlier, but do you know why our B value of 0.17 did not show growth? If you look back at your notes, we mentioned a couple of times our B value has to be bigger than 1 in order to grow. It just has to be. Otherwise, we are not growing. So what can we do? Well, think about it like this. If our B value is bigger than 1, it grows. If it's less than 1, it shrinks. What happens at exactly 1? Well, if we were multiplying 31 by 1 to anything, let's see what would happen. If we took, for instance, y equals 31 times 1 to the 7th power, that's 31 times 1 times 1 times 1 times 1 times 1 times 1 times 1. That's just 31. When you take something like 1 to the 7th power, it doesn't change. So the difference between growth and decay is growth is above 1, decay is below 1, and by keeping something at exactly 1, that will let us stay where we are. In this problem, do the 31 bald eagles ever really decrease? Not according to the problem, no. According to the problem, these 31 eagles we're assuming will stick with this population. Granted, I know that's not realistic. I know that life and death is a thing, but for the purpose of this problem, we want to stay at least 30 eagles, right? So we have to guarantee that our number is at 1, and then 17% more showing growth. To show that we start at 1 and then get 17% more eagles, we will write 1 plus 0.17. And we're taking it to the 40th power again. This is the secret of exponential growth. If you look at your notes, down below at the bottom of the page, we actually have a function that looks like this. We're going to talk about the letters in just a second and generalize this, but for now, let's finish this problem because I'm curious to see how many bald eagles there were. If you think you can simplify this using PEMDAS, go ahead and try it. You absolutely can. If not, you can follow the video. But again, try this out if you are able. If you just want to see how it's done, let's take a look. In parentheses, which is the first thing we have to solve, we have 1 plus 0.17. That's 1.17. We take that to the 40th power by pressing our x to the y button, 40, like so. And don't forget, this is just this part. We still have to multiply by 31 at the end. According to our math here, this is a much more optimistic number. According to our math, in the year 2022, if we kept growing at a rate of 17%, there would be 16,549.9300 eagles in Michigan. It's a pretty good number. Let's make sense of this, though, because we can't write 549.93009. Something about this doesn't make sense. And it has to deal with our units. I cannot write today. I apologize, y'all. Would it make sense to have 0.93009 bald eagles? It wouldn't. Your problem will often tell you how they want you to round. But in general, here is the rule. If your problem doesn't tell you to round to the nearest blank, look at your units to determine how much you should round. In terms of bald eagles, can we have 0.93 of a bald eagle? No. So we would either round up or round down. You could say there will be 16,549 whole bald eagles, or you could say there would be about. Y is about 16,550 eagles. Unfortunately, if you do not want to be depressed, I would not recommend looking up the current number of bald eagles in Michigan. Due to environmental impacts, they did not keep this 17% every year rate. The good news is they have helped us out here today with discovering how to describe exponential growth functions. Exponential growth functions are written out like this. It's the same as before. We're still going to have our a value. But instead of a b value, we want to be specific. We want to stay the same population and grow by a certain percent. To represent this, we're going to do 1 plus our rate of change. But we can't use b. We can't use b, because b is our whole growth factor. In the problem we just did, for instance, our value for b would be 1.17, because 1 plus 0.17 is 1.17. Instead of using b, we are going to use the letter r. Finally, instead of using x as our exponent, we're going to be more specific and use t. Well, before we get too ahead of ourselves, let's talk about each piece. A is still going to be your initial amount, your y-intercept. We started with 31 bald eagles, so 31 went into the spot for A. R, we call a very specific constant. We're going to call R our rate of growth / decay. And the important thing is, our rate cannot go in here unless it is a decimal. So remember how we turned 17% into 0.17? It has to be that way. It must be a decimal. Finally, our t, you may predict, is time. When we're talking about exponential growth and decay, we are talking about it in terms of time. Your time can be minutes, or hours, or seconds, or days, or years, or decades, or eons, but it has to be a unit of time. Let's try something out real quick. If we flip over to page 187, I want us to take a look at problem number 7. Problem number 7 asks us to figure out if a function represents exponential growth or decay, then determine the percent rate of change. Okay, well, first off, we have our normal form here. Y equals a b to the x. In this case, it's to the t. These forms are interchangeable, meaning you can switch from one to the other as often as you like. When there's a t involved, you know that they want a little bit more specificity about our b. So why would this be growth or decay? If our b value is bigger than 1, it's growth. So b is bigger than 1, growth. But it doesn't just ask us that. It asks for our percent rate of change. Not our growth factor, our rate. Uh-oh. We have 1.08. We can't turn that into a percent easily. You can, but it'd be 108%, which is weird. When they ask to identify the percent rate of change, they want this hidden R value. Remember the formula we used? A equals 1 plus R to the t? They want the R. Uh-oh, we're not given a 1 plus something in here. This is where you need to dissect your growth factor. If your growth factor is 1.08, you have to ask yourself how much that's really growing by. 1.08, we can rewrite in terms of 1 plus something, right? In fact, if we rewrite our problem, y equals 500 times 1 plus something to the t power. What's that something that'll make 1 plus something 1.08? Well, it'd be 1 plus 0.08. 1 plus 0.08 is 1.08. So our value for R in this problem, R equals 0.08. Can we turn that into a percent? Remember our rule. The rule is to turn from a decimal back to a percent, we go 2 decimal places to the right. So this would be 8%. That's an 8% rate of growth. Be very, very careful. If you see one number in parentheses, that is your growth factor, just like we talked about in the last unit. That doesn't change. But you can always write your growth factor as 1 plus, or at least some variation of that, your rate. You can always rewrite a growth factor bigger than 1 as 1 plus your rate. Let's take a look at problem number 1. I think we now have everything we need to try this problem out. In 2005, there were 100 rabbits in Polygon Park. The population increased by 11% each year. We want to write an exponential growth function that represents the population t years after 2005. That means in our function, we do not want to fill in t for something else. We're just going to write it as t. Important piece of information to note. At the start, there were 100 rabbits, and our population grew or increased by 11%. I want you to try this problem out on your own. Pause the video here and come back once you are ready. Did you try it? Let's take a look together. We are going to want to use our exponential growth formula, y equals a times 1 plus r to the t power, in some variation for this problem. We can tell it's growth because of the word increased. So what do we plug in where? Well, we don't know the number of rabbits after t years. That's y. That's our answer. A is our starting amount. So we're going to put 100 rabbits in for A. Inside of your function, it's always going to be 1 plus something. But the problem is we don't know what that something is. Well, if our population is increasing by 11%, let's turn 11% into a decimal. By dividing by 100 or taking the decimal place, 2 to the left, we'll find 11% is 0.11. So we write it as 1 plus 0.11 to the t. This would be fine But big ideas would want you to simplify. So when we simplify this problem, what can be simplified? Well, 1 plus 1.11 would just be, 1 plus 0.11 is 1.11, a lot of ones to the t power. Can we simplify further? Tricky question, but we cannot. The reason is because we don't know what t is, and normally we would have to take 1.11 to the t power first, before we multiply it by 100. This is our final equation. Simplify as much as you can. Now, we take this question to a new dimension. What will the population be in 2025? And we want to round our answer to the nearest whole number. Uh-oh. Well, will we put 2025 in for t? No, because 2025 years have not passed. If 2025 years passed these rabbits, we would not be living on a planet with soil anymore. We'd be living on a planet with rabbits. So what do? We have to know what year we started in to know how much time has passed. And we started in 2005. So what's 2025 minus 2005? It's 20 years. So our value for t will be 20. In other words, we are going to be solving the following. Y equals 100, 1.11 raised to the 20th power. To figure out what this is, we'll need to bust out the calculator once again. So, bringing out the calculator, the first thing we need to do is multiply, well, not multiply, we have to take 1.11 to the 20th power. We're multiplying it by itself 20 times by taking it to the 20th power, giving us this number. We then multiply by 100. Do not forget to multiply by the number at the start. That number still exists. And we get 806.23. And since we wanted to round to the nearest whole number, we would say there were 806 rabbits. That's it. That's how you solve problems with exponential growth. Let's go back to our notes for a brief moment before we continue. We've talked about exponential growth, but what about exponential decay? Well, we know what exponential decay is. It's sort of the opposite of growth. Exponential decay is when a quantity decreases by the same factor over time. So it's similar but different. Also keep in mind that in order to decay, our b value had to be in between 0 and 1. If it's negative, it's a no-go. So, if we are exponentially decaying, we are going to be decreasing our functions. Let's take a look at a different example here. So here's the problem. The value of Mr. Strager's Lamborghini is $208,000. It loses 12% of its value each year. So the question is, how much will my Lamborghini, which I totally have, be worth in 10 years? This is a little bit of a tough one. Well, we know our formulas. We have a couple of them that we can use. We have our y equals ab to the x. And we know that when we're growing something, it'll be y equals a to the 1 plus r raised to the t. This is not growth, though. We're losing value each year. This would be decay. So we want to figure out how to use this percent in a decay function. Well, keep in mind that with this car, we're still going to base its value off of whatever the value was the last time. We still want to use 1 somewhere in there for this. But would it make sense to do 1 plus 12%? I don't think so, because that would be growth. So what can we do between this 1 and the r that would make sure our growth factor is less than 1, or in between 0 and 1, I should say, we can subtract. And this is the exponential decay function. Notice how slightly different it is from the exponential growth function. Y equals a times 1 plus r to the t. Y equals a to the 1 minus r raised to the t. So let's plug in what we know. We don't know y, so it's going to stay y. Our starting amount is $208,000. What can I say? I've got expensive tastes. We need to figure out what our rate is. Well, here, we lose 12% value each year. So, to turn 12% into a decimal, we can divide by 12 or move the decimal twice. I moved the decimal last time, so let's divide this time. 12 divided by 100 is 0.12. So this would be raised to the t. And when we simplify our growth factor, what do we get? Well, 208,000 is going to stay the same. But 1 minus 0.12 will give you a decimal, 0.88. This function here tells us we're keeping 88% of its value. That's why we do 1 minus 0.12. It's not dropping down to 12% of its value each year. That would be like saying it goes from 208,000 to being worth 20,000. It's not the case. We're only dropping by 12%, meaning we're staying at 88% of the total value, or 0.88. That's why we have it as it is. So let's solve this after 10 years. After 10 years, that means our t value would be 10. Try simplifying this one out on your own. Pause the video, try it out. Hopefully you had a chance to pause. Let's do it together. To solve this, we're going to take 0.88 to the 10th first, because exponents come first, after parentheses. Boop. We end up getting this number. We then are going to multiply it by our starting value, 208,000. And our final value, okay, this is still not bad after 10 years. It looks like after 10 years, my car, my Lambo, still going to be worth a good $58,000. But we have to be careful with rounding. What is the unit we're talking about here? Dollars, right? Well, in terms of money, we always rounded 2 decimal places. So this would be $57,928.20. There we go. That's how much money my Lamborghini would be worth after 10 years. Of course, my endless salary, I would absolutely be able to buy another one in that time. But regardless, we've calculated it. So exponential decay is a lot like exponential growth. In fact, it is so similar, the only thing that changes is we change from plus to minus. There is one thing that gets a lot harder with exponential decay. Let's flip back to 187 and go to question number 6. Question number 6 asks us if this is growth or decay, and to identify the percent rate of change. Well, again, we look at our b value. It's 0.95. So our b value is in between 0 and 1. It's going to be decay. Cool. But how much is decaying by? Keep in mind, the growth factor, when it's below 1, is how much of the original value you are keeping. So this is not saying we're dropping by 95%. No, no. Remember, an exponential decay function will be written out like this. 1 minus r to the t. In other words, 0.95 is 1 minus r, or 1 minus something will give us 0.95. What is that something? There are a couple ways of solving this. If you want to solve it algebraically, given that this is algebra class, well, 0.95 and 1 minus r should be the same thing, right? They're equal to each other. You could set up an equation like this and solve. Another little trick to give you is this. 1 minus your rate equals 0.95. But also, 1 minus 0.95 will equal your rate. It's a weird math trick where you can swap the r and the 0.95. This only works in very specific circumstances. What is 1 minus this number in parentheses? We get 0.05, which as a percent, when we move it twice to the right, we get 5%. This is a 5% decay. This is the toughest part for a lot of people. So I'm going to put up another quick one just for you to check in on. Let's say I gave you the following. Y equals 3 times 0.34 raised to the t. And I want to figure out what my percent rate of decay is. Well, you can do 1 minus r equals 0.34, or you can use the trick that we found out, which is that you can swap the r and the 0.34, again, this only works in certain cases, don't try to replicate it everywhere you go, to figure out what r is. Either way we do it, r will equal what? 0.66, or 66%. That is a key to note when you are trying to identify the percent rate of change. All right, there's one last thing we're going to talk about, and this is probably one of the most important things that we are going to be talking about. In general, a lot of students ask, Mr. Strager, when am I going to use this in real life? Mr. Strager, can you teach us about taxes? And unfortunately, the main problem with teaching a lot of life skills is you have what you need already. You learned it in middle and elementary school. For instance, to do taxes, you just need to be good about managing documents and knowing how to add and subtract. That's taxes in a nutshell. However, there is something we're going to talk about today that is very important for adult life that does have to deal with what we just talked about. And that is interest. You may have heard the word interest, but let me put it simply. We're talking about banking here. So, when you go to the bank and you give them your money to deposit, what do you think happens to that money? Oh, they don't just store it for you. They don't just keep it in a box labeled with your name on it. The bank is actually going to use your money to invest. Meaning, the number that you have in your account is imaginary. They might not even have that actual amount of money in the bank with them. However, when you come back to the bank, you are expected to be able to come back and retrieve your money at any time. That's the expectation. So, let's say we deposit $10,000 in the bank. Well, why would I deposit my money in a bank if I know they're just going to use it and there might be a chance I can't get that money? There is a thing that the bank does called interest. Interest is basically the bank paying you to keep money with them and to stay loyal. So Chase Bank or Fifth Third Bank or the Fifth National Bank of Mr. Strager will say to you, thank you so much for your $1,000 deposit. We will hold that nice and safe for you. As an exchange for keeping your money with us and not Huntington or Bank of America, we're going to give you a little bit of something something. Buy yourself something nice. They'll give you money based on how much money you have with them, because that shows the amount of trust you have in them. If we deposit $10,000 in the bank, they might say something along the lines of, you will get a % yearly interest rate. So let's go with 0.05% yearly interest. This can mean one of two things, depending on the type of interest. But basically, what this means is every year, they'll give you 0.05% of the money, what that means we'll talk about in a second, back to you as a thank you. You're welcome. If we go and take a look at what this means, there are two types of interest. Simple interest is the type that we basically just talked about. We deposit $10,000 in the bank, and we don't touch that money. The bank agrees, and they say, okay, we will give you 0.05% of that every single year. So, year 0, I'm going to make a little bit of a table here. In year 0, we would have $10,000. Well, to figure out how much money we have in year 1, let's figure out how much money they're giving back to us. That would be $10,000 times whatever 0.05% is as a decimal. This is still a percent, despite the fact that it looks like a decimal. We have to move the decimal 2 more places to the left. So this is actually going to be times 0.0005. Oh boy, we do not have a great interest rate. If we're getting 0.05% or 0.0005 back, we're going to multiply that, and this is how much money we get at the end of the year. A crisp, clean $5. Not much. And banks usually don't give you a ton, unless you deposit quite a lot of money in them. So, if we add $5 to our account, after year 1, we would have $10,005. And simple interest is where that same interest rate will keep on going on and on and on and on. We didn't touch our money, so they'll give us another $5. And they'll give you another one after that, and another one after that. And every year, we are going up by 5 smackaroos, 5 doubloons. Not a bad deal. Definitely not ideal, but not a bad deal. So after 4 years, we would have made $20 just by putting our money in a bank. If you get a 0.05% yearly interest rate, well, depends on how much money you put in, but you might want to seek out more. This is simple interest, and the idea is, based on how much money we put in or take out, this amount right here, that determines how much money they give us each year. If you are ever given the same rate for compound interest, go with the compound interest instead, and I'm going to show you why. Compound interest is very similar. Our yearly rate is still the same, our deposit is still the same, so I'm going to make the same table, going from year 0 to year 4. And, as always, in year 0, I started with $10,000 in the bank. And if I'm making 0.0005 yearly interest, I'm getting $5 again. But this is where compound interest is special. You see that $5 of interest that's added to our account? Well, compound interest says, that's your money now. So why not count that as the thing that we're taking interest on? In other words, instead of just multiplying 10,000 by 0.0005 again to get your interest and the same $5 again, we're going to change things up and multiply 10,005, since that's the new amount you have in your account, by that amount. In this case, we're making $5.0025. Still $5. Nothing too special here. The difference is, we're technically making a little bit more. Of course, we don't actually make 0.0025 of a dollar. That'd be like a quarter of a penny. So it's not much when your interest rate is this low. And in fact, I chose a really bad example because this is a really low interest rate. But we would have $10,005 and 0.0025 cents. The difference is, we're now going to use this amount. So I'll add in, oh sorry, this would be 2,000, sorry, I apologize y'all. This would now be $10,010. So when I take together my 10,010.0025, I'm going to multiply this by 0.0005. Now I'm at 10,000, or I get $10 and 0.0075 cents. Now the amount of money is super increasing. Now I'm going up by $10. You see where the picture is going? The idea is compound interest. You get more money the longer your money is in. Your interest develops interest. So this would be $10,020. And in fact, we've just earned ourselves our first official penny. Woo! You see where this is going? In 3 years, we made as much with the compound interest as we would have in 4 years with the simple. This is very, very, very nice. Charging interest on your interest means that the amount of money you gain goes up and up. Here's a little informational tidbit for you as well. You may have heard the name Paris Hilton before, the daughter of the person who created Hilton Hotels. Well, Paris got a lot of her money from investing in the bank. Paris took her father's wealth when he passed away and said, which bank is going to give me the most money in interest? And she invested in them. By doing so, she was actually able to live many years of her life, I want to say 15 to 20 years of her life, without having to do anything. She just lived off of the amount of interest she was getting. She didn't need to touch her money, add anything to it, nothing. She kept her amount of money the same. She lived off of just the interest. Of course, to do this, you're going to need a higher percentage and a higher deposit. But the idea is still there. There is a formula for calculating interest, specifically compound interest. The formula for simple interest is very easy. You can look it up and you'd be able to process it through in just a minute. Compound interest formula looks a little bit strange. Again, at this point we've talked about a couple of equations. We've talked about growth, we've talked about decay, and we've talked about our basic exponential, and they're all related to each other. They all look the same. Compound interest is no different, but it is going to have a couple more variables. The compound interest formula is y equals p times 1 plus r divided by n to the nt power. This is the compound interest formula. And you might be saying, Mr. Strager, what? Don't worry. It looks more complicated than it actually is. In this formula, instead of using a, we use p. But p is the same thing. It's your initial amount. It just so happens that in banking, your initial amount is called the principal. The amount of money you put in at first is called your principal. R is still our rate. But it's not just going to be a rate. We're going to call it our annual interest rate, meaning how much percent we get per year. T is going to be time, but it's more specific than that. Here, T is time in years. Previously, time could be anything. It could be months, seconds, eons, whatever. Specifically with compound interest, it is years. Finally, last but not least, N. N is the number of times per year the interest compounds. Oh yeah, I'm throwing a curveball at you here, folks. N is the number of times per year your interest compounds. You don't need to get your interest just once per year. In fact, some banks will give you offers where you can get it once per month, or once per quarter, or maybe even once a day if you get a crazy good bank. But I don't think there are many banks that do that. Compound interest could be over any length of time as long as your rate, R, and T time are in years. Let's talk about that very briefly. If you flip the page to page 186, you'll see a much neater version of what we just talked about. And down below that, I want you to make a brief table. I want you to write down time and N. The amount of times it'll be compounded per year, they usually won't say, oh, it's compounded 17 times a year. That's a weird number. It's usually broken up a couple of ways. If you get your money annually, that means you're getting it once per year. How many times do you think you're getting it if you're getting it semi-annually? Think of this. How many semicircles does it take to make a full circle? Takes two, right? It's the same here. Semi-annually, or the word semi, means half. So you get it every half year. Maybe you get a payment on interest in January and July. That would mean your N value, here and here, would be 2. What about quarterly? This is one that most people can be familiar with. Quarterly means you're getting it every quarter of a year, or 4 times per year. Maybe once in the winter, once in the spring, once in the summer, once in the autumn. What if we said you're getting your interest monthly? How many times per year would that be? Well, there are 12 months in a year, so you'd be getting it 12 times. What about weekly? 52 weeks in a year, so you're getting it 52 times. Daily? 365. I almost did 56. 365 days in a year, approximately. This is terrific, because now we have a way of solving compound interest problems. What I mean by that is this. Let's turn to the next page, page 187. On page 187, at the very bottom, we're going to take a look at problem number 9. Now, the way you can tell you are dealing with a compound interest problem, this is very important, very hard to keep track of, is if you have the words compounded and interest. I know, crazy. But you'll be surprised how many times you ask yourself, is this a growth, is this a decay, is this a regular exponential, or is this a compound interest? Only use the compound interest formula when you see the words compounded and interest. Otherwise, don't do it. It's probably not the right formula. So the formula for compound interest, again, is y equals p instead of a, 1 plus r over n to the nt power. Let's fill in some values. Do we know our principal or starting amount? We do. We deposited $3,000, so 3,000 is P. We're always going to keep that 1 plus. Exponential growth, right? We're always growing our money. What about R? Our rate here is 6%, but we want to turn it into a decimal. 6%, if we do our little trick by moving it twice to the left, is 0.06. So 0.06 is our rate. Divided by n, well, how many times are we compounding? quarterly, so 4 times per year. And don't forget, because a lot of people will, n is also up here. It's in 2 places. So that's going to be to the 4t power. Big Ideas will want you to simplify what's in parentheses, but you are not required to do so for today. But again, you may have to simplify parentheses here and end up with something a little weird. If you do so and you want to check your answer, just to make sure you've got it 100% right, your answer for the final bit should end up being 3,000 times 1.015 to the 4t power. All right, everyone, that is it, finally, for these very long 6.4 notes. That means we are ready for our Unit 6 test, since we're not covering 6.5, 6, or 7. As always, I hope you have a fantastic rest of your day.